So at this point we've covered work, and we're going to move on to look at energy. We'll start by defining kinetic energy, which has to do with objects in motion. So I'm going to start by deriving the equation that expresses kinetic energy. We can look at this work equation, work equals force times displacement, or delta x, and now we're going to plug in ma for force. So now this F becomes ma times delta x. We can also go back to this velocity equation, where v final squared equals v initial squared plus 2a delta x. If we isolate the a delta x, and then plug it into this equation, where we also see an a delta x, we get that work equals mass times v final squared minus v initial squared divided by 2. Or in other words, 1/2 mass times the change in velocity, or delta v, squared. So we'll say that the equation for kinetic energy is 1/2 mv squared. Let's see how that works in problems. So energy is similar to work not only in that their equations are related, but also in that energy also uses the unit joule, or capital J. Kinetic energy is a scalar quantity, and it depends on both the speed and the mass of an object. So I think we've already seen from the equations that work and kinetic energy are kind of related. This theorem shows how. The work kinetic energy theorem states that the net work on an object is equal to its change in kinetic energy. So for example, if there's work done on this block down here, the speed will increase, or in other words, its kinetic energy will increase. An additional type of energy is potential energy. This has to do less with the object's properties and more with its shape, condition, or position. In other words, its interactions with its environment. So here we have two examples. We have a ball that's falling off a cliff, and we have a block that's being stretched on the end of a spring. Neither of these objects moves as a result of their own characteristics. However, the height of the cliff causes the ball to fall to the ground, and the stretch in the spring causes the block to move. Let's take a look at how these two situations work. The first type of potential energy is known as gravitational potential energy. This is energy stored in the gravitational fields of interacting bodies. So for example, in this situation we have a roller coaster that's at the top of a ramp. It's going to speed up as it goes down the ramp as a result of the energy that it got from being at a height that's higher than ground level. So gravitational potential energy depends on a few factors. It depends on mass of the object, the height of the object, and the rate of free fall acceleration, which we've defined as g, or 9.81 meters per second squared. We can combine these factors into the equation for gravitational potential energy. Gravitational energy, or E sub g as we'll call it, is equal to mgh. Now as you can see, only one of these parts of the equation is actually a property of the object. The mass, here we labeled it object to show that it's related to the size of the object or the material it's made of. However, gravitational acceleration and height are both products of the object's environment. Therefore, gravitational potential energy derives a lot of its quantity from the conditions surrounding the object. Another type of potential energy is elastic potential energy. This is defined as energy available for use when an object returns to its natural position. So let's look at what that means. In this example, we have an object that's being stretched on a spring. The spring in this first diagram is very stretched out. In other words, it's storing lots of potential energy. This energy will be released when the spring is let go back to its natural position in the second drawing. We have an equation for elastic potential energy as well. We have E sub E, that'll be what we use to describe elastic energy, is equal to 1/2 kx squared, where k is the spring constant, which is usually a given value. That's measured in newtons per meter. And x is the length of the stretch, or in other words, the distance that the spring has been moved from its natural position. We'll do some practice problems with energy. Number 1. A spring with a force constant of 5.2 newtons per meter has a relaxed length of 2.45 meters. It is stretched to 3.57 meters. What is the spring's elastic potential energy? So we're solving for elastic potential energy, or E sub E. We know from the last slide that the equation for that is 1/2 k times delta x, or the stretch position, squared. Now we can plug in the numbers we have to get that this is 1/2, the spring constant is 5.2, and delta x is the difference between its final position and its initial position, so that's 3.57 minus 2.45. We square all of that. I'll plug in these numbers, and we get that the elastic potential energy of the spring is 3.26 joules. Number 2. Calculate the velocity of a 10 kilogram block with a kinetic energy of 400 joules. This time we're looking for kinetic energy, or EK. We know that that equation is 1/2 mv squared. So in this case, they've given us the final kinetic energy. That's 400 joules. And we'll set that equal to 1/2. The mass of the block is 10, and we're solving for velocity. So we can simplify. That's 400 equals 5v squared. Divide both sides by 5. We get that v equals root 80, or 8.9 meters per second. That's the velocity of the object. Number 3. A student is pushed across an ice rink with a force of 45 newtons. How far must she be pushed so that her final kinetic energy is 352 joules? So in this case, we're looking for kinetic energy, but this is slightly more complicated because we're also combining work. So we've defined work as force times distance, and we know that the work that's performed on the girl will be equal to her kinetic energy because of the work kinetic energy theorem. So now let's plug in some values we have. We know the force, that's 45 newtons. We're looking for the distance, or how far she must be pushed. And that will be equal to kinetic energy, which we've been told is 352 joules. Now we can divide both sides by 45. We get that the distance she has to travel is 7.8 meters across the ice rink. Number 4. A 40 kilogram child sits on a swing with ropes that are 2 meters long. What is the child's gravitational potential energy relative to the bottom of the swing under the following conditions? So we've learned from before that gravitational energy is equal to mgh, or mass times acceleration due to gravity times height. So if the ropes are horizontal, the height of the child on the swing is going to be 2 meters above the bottom of the swing, as I've labeled. So now we're solving for gravitational potential energy. We know that the mass is 40 kilograms. G we'll call 10 for the sake of making this calculation easier. And the height is 2 meters. We multiply that out, we get that the energy due to gravitational potential is 800 joules. In the second scenario, the ropes make an angle of 30 degrees with the vertical. Now the height above the ground is much smaller. So in order to find this height, h, to plug into the equation, we'll do 2 meters, that's the bottom of the swing, minus 2 cosine 30 degrees. That's this other part of the rope that we're subtracting because that's not part of the child's height. So if we plug this into the equation, now we get that the gravitational potential energy is m, still 40, times g, which is still 10. Now we call h 2 minus 2 cosine 30 degrees. Plug all of those numbers in, and the gravitational potential energy is now only 107.2 joules. Finally, if the child is at the bottom of the swing, well, now we know that the height relative to the bottom of the swing is 0, because the child has reached the bottom of the arc. So, if we plug in mg and h, we get 40 times 10 times 0, or in other words, 0 joules of energy.